So in this video I'm going to talk about the resistor as my previous video was also talking. So in the previous video I made it about a series. In this video I'm going to make about a parallel. So it is very interesting to study about this in the app called as Proteus, application called as Proteus. I don't know what it is called as. So oh yes, it is called as a software. Hmm. It is a software where we can simulate the circuits. So let me make a new project here. I will make a new project. We can browse here. I already told how to use it. So I'm going to browse it in my files. So here I have made something. So this I have chosen, and then I will change the name to resistor 2. You can keep it name whatever you want. I want you to try this yourself. So everything else is going to be default, and we will go inside this area where we can simulate the circuit. Now to simulate the circuit, first I will take the resistor. To take the resistor, I am going to press the P on the keyboard. Then I will take the resistor. Then I took the resistor. Okay. So this is a single resistor. I want one more resistor because I'm going to connect them in a parallel. So this is what two resistor. I will change their values only to 1 ohm for the simplicity. So the changing is very easy. Double click on that resistor and 1. Same thing I will do to the second resistor. Then it is going to be 1. Now to show the series and parallel connection and voltage relation and current relation, I will take one voltage source. Again I will press the P, then I will search the voltage source. That is DC voltage source I'm going to take, and I'm going to connect it. Let me take it. Then I took it. To make it more good clarity, I will rotate it. Now I have rotated in the wrong direction. Let me rotate it again. Again I have rotated in the wrong direction. So this is the correct one. So now let me connect this to these resistors. I'm going to connect them parallel. What is parallel? One end is connected to the other. Let me make this wire bigger so that it will be very clear. So I'm going to take it here, then I'm going to take it here. So this end is connected to this end. This is known as parallel connection. But if I leave it in this way only, it is series connection. I have to connect another end of this resistor to another end of this resistor. So this is called as a parallel connection. So the parallel connection equivalent resistor formula is what? Now here is R1 and R2. So R equivalent, that is total resistance in this connection, is R equivalent is equal to R1 into R2 divided by R1 plus R2. So this is a formula to calculate in the parallel connection. In series it is directly R1 plus R2. So now let me connect this voltage source also. So let me connect it. Okay, I have connected it. Wait. So this I have connected and kept the voltage value as 1 volt. So for simplicity we are going to keep everything as 1. So this is a parallel connection. You might be seeing whatever the voltage is here, whatever the voltage difference between these two nodes is going to be 1 volt, because we can already see in that in parallel we have connected it. Whatever this wire and this wire difference is going to be same to this wire and this node, and this node and this node. So one thing you can observe from circuit itself, that in parallel connection the voltage is going to be same across R1 and R2. For to show it more clearly, I'm going to connect an voltmeter there. Let me take a voltmeter now. Here is the voltmeter, DC voltmeter. I will take it. Okay, I'm going to connect it in parallel. Okay, I have took it. One wire is connected here, another wire I'm going to connect it here. I'm going to take one more voltmeter because to make it more clearly. You might feel what I'm showing. So I will connect it here. No, the wire should be clearly visible. So I have connected one more wire here. One more wire I will connect it here. So I have connected voltmeters across both the resistor. Now let me run it. Before running, I am going to tell what is the value, that is 1 volt. I have already told in parallel the voltage remains the same. So let me run it. So it is running. You might be seeing 1 volt, 1 volt. Now I will change the value of resistor, then also the value is going to remain same. Because whatever you do, but the point is connected here itself and 1 volt is connected at this point itself. So there is no change of voltage. Whatever you do, the resistor's value changes. Like I will do the value of this resistor as 2 and I will keep that as 1 itself. Now let me run it. See, still it's a 1 volt. It's a very clearly visible. Yes, it's a still 1 volt. I have made it as 2 and this has been 1. But what changes you might see by changing this resistor's value? One thing which is visible very clearly is that the value of current is going to be changed. So always remember, in series the value of current is going to be same, and in parallel the value of current is going to be changed. One resistor has a one current value and other resistor is going to have another current value. But in series there is what is going to be remain same, that is current, and what is going to be changed, that is voltage. One resistor will have another voltage drop and one more resistor will have another voltage drop. But if the resistors are equal, that is a different case. If resistors are equal, both the resistor will be having the same voltage drop and current will be also be same. In parallel also, if the resistors are equal, both the resistor is flowing with the same current and same voltage. So that is a different thing. And one more thing, in the series connection I have given one shortcut formula for to find the voltage across any resistor. In the same way, I am going to give one more shortcut formula to find the current across any resistors in connected in parallel. So now let me give that shortcut formula. To find the current across, first we will find the total current in the circuit. To find the total current in circuit, we have to know the equivalent resistor value. I have already given the formula for equivalent resistor value, that is R1 into R2 divided by R1 plus R2. So R1 into R2, let me make this value as 1 itself back to make the simplification of calculation. I have made it 1 back. So R1 into R2 is going to be 1 into 1 divided by 1. So it means the equivalent resistor value is what? 1 into 1 divided by 1 plus 1, that is going to be 1 by 2, that is 0.5. So there is one more shortcut formula to find the equivalent resistance in parallel when the resistor value are equal. When the resistor value is equal, we can take R by 2, that is both the resistance value is equal, that is 1. So 1 by 2 is going to be 0.5. Directly we can say this way also, if the resistors value are equal. So this is also one of the shortcut for to find the equivalent resistance when the resistance value is equal. So now we got the resistance value as what, 0.5 ohms, and we are having the voltage, so that is 1 volt. So I is equal to what, V by R. So I is equal to V by R. V's value is 1 and that is 0.5. 0.5 is nothing but 1 by 2. So we are going to get the current, total current of 2 amps. What does it mean? From this strand we are going to get the 2 amperes of current. So to show that also that I am correct and my calculations are correct, I am going to show one more thing by connecting an probe. Here is a probe mode we are going, and we will take a current probe and we will connect it here. By this we can see the current value also. Let me run it. No, there is an error which is coming. R22 is ambiguously placed. I don't know why it always by connecting probe it happens. Let me see one more time by connecting it. I will connect it here. Let me see what does it give again, error. No, it is not giving error now. I don't know by connecting what happened here. Let me connect it somewhere else so that we can see the value clearly. There we are not visible it is. So let me take the probe and I will connect it here. See, ah, see, you are visibling the current value has -2. Okay, current value is 2 ampere. Direction must be I guess the direction here it is in this way, but actual direction is this way, so it is giving as a -2. If I connect it, okay, it is -2. Why? Because the probe's direction is been showing this way, but actual direction is this, so it is showing the -2, but the value is 2 amperes. So according to our calculation it is also verified. If you see that resistors value are 1111, so the current is going to divide it equally, that is here 1 ampere and here 1 ampere. That I will show by connecting the same probe. I can also show that by same probe, or I can connect the ammeter. It is both the cases are same. I will connect to the probe and I will show it. So now I'm going to connect a probe here one. Let me run if it gives some error. No, it is not giving. So let me connect the probe clearly where the value is visible. Okay, I will connect the probe here one, and one more probe I will connect. Yes, at this place. Now let me run it. See, the current value is going to be 1 ampere and 1 ampere. Okay, the current value is 1 ampere, 1 ampere. Now let me change the value of second resistor or any one resistor. I will change this value to 2. Now again we have to find the total resistance again, that is 1 into 2, 2, and divided by 1 plus 2, that is going to be 3. 2 by 3 is the value of total resistance, and V is 1 itself, so 1 divided by 2 by 3, that is going to be 3 by 2. 3 by 2, the total current is going to be 3 by 2. So it's going to be 1.5 amps is going to be total current in the circuit. Okay, now we have to find the resist value at R2 and R1. So I will going to give one shortcut formula for that. If I want to find the current through R2, so we know the total current, that is going to be 1.5. So it is going to be into total current into the resistor which is parallel to the resistor. So now the R1 is here, we want to find the current through the R2. So we are not going to multiply the R2, we are going to multiply the R1. In voltage it was different, wherever we want to find the voltage, that resistor value we were multiplying. It is here different, that is we are going to multiply the R1. So the total current into 1, total current into 1 divided by both the addition of resistor, that is 1 plus 2. So the value is going to the value of current across R2 we are going to get by doing this. So let's do it. So by using that formula, the value of current we are going to get at R2 is going to be 0.5. So what we should do, that is total current into R1, whatever the another resistor which is remaining in parallel, into R1 divided by R1 plus R2 is a formula to find the current across R2. Same thing we can apply to R1. To find the current at R1, we are going to do it as total current into R2 divided by R2 plus R1. So this is going to be the formula. By doing this, the current across R2 we are going to get it as a 0.5. So total current was what? 1.5. So 1.5 minus 0.5 remains with a 1 ampere. So that 1 ampere is going to go with through the R1. So here there is one more thing we can know, that is about the Ohm's law. So what does the Ohm's law says, that is V equal to I into R, and I is equal to what? V by R. As the resistance is increasing, current is going to decrease. So R2 value is 2 ohms. So the current will be less than the R1. So that is why the R2 is getting the lesser current, that is 0.5, and R1 is getting the more current, that is 1 ampere. This also can be understood by using this Proteus, very useful tool which is made. So now let me run to verify our values. So I have said that R2 is going to go through the value of 0.5 and R1 is going to 1 amps. So let me run it. So it's a very clearly visible, the total current is 1.5 and R2 is having zero point 0.5 and R1 is having 1 ampere. So this verifies the Ohm's law itself also. So basically the R equivalent was also derived using the Ohm's law itself. And whatever I'm telling, the two laws, that is voltage, two rules, that is one is voltage divider rule, one more is current divider rule, all are basically based on the Ohm's law itself. So Ohm's law is the main important rule in the electrical stream. So always go with a basic. So that's it for today. Thank you.